This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
You will be seeing low frequency and then so many frequency components, even very high frequencies, and then only you get a 10 nanosecond.
Yeah.
If you remove some of the high frequencies, then what will happen? You are removing. Like you are going to put this through a low pass filter. Like this. Then you are going to remove some frequency components. Then what you will get here is, maybe it will become 100 nanoseconds because you already removed some frequency components. But then, if you further remove, again it will spread it. So that this sharpness or the width is depending upon how many frequency components you got. So if you got infinite frequencies, you get a delta function. That is not possible. That's what is the concept. If you take a square wave, if you take a FFT, you will get so many frequency components. If you remove some, what will happen? Then it will become like this. You know what I meant? Sorry?
It's wider.
Yeah, in square wave, if this is in the nanosecond, it will become wider. But if it is in the millisecond or something, then you will not widen here, but it will start going like this.
Okay.
Yeah, you know what I meant? Nanosecond, you can see the change quickly. But if it is in the millisecond, you will see the change here in these edges. Because here it is very, very small.
Okay.
Yeah.
Okay.
Yeah.
We still cannot select the session.
Yeah, but then this will appear maybe after an hour or two because we just opened the workshop. You might have seen the announcement. Yeah. I think please wait maybe 1 or 2 hours. Yeah, because it might take some time in the system to appear. And then if you have any other issues, we will sort it out. Because today is only Monday, so in the coming days, because some students might enroll to this one, and then also some students can move from the existing workshop to this one, so that we can and we can accommodate the students if there is a clash. Yeah, it will come after some time maybe. Okay, we will start then. So we have got a very sensitive equipment, something like a laser diode. So we got a laser diode. So that is called LD. So that is called a laser diode. So this laser diode require maybe 10 milliamps. So the laser diode operation is 10 milliamps. So laser diode is the best example for a current source. And then you have to keep 10 milliamps. If you are operating at 10 milliamps and if the current is fluctuating, this laser diode will be damaged. So you need something that will keep 10 milliamps. So if you are doing something like this, you got a battery or some power supply, then what you do is you connect a resistor, then you connect your laser diode, and then you connect to the ground. Maybe this is 10 volt, and then if you want 10 milliamps, how much you need? Sorry? Yeah. So depending on the voltage, and then you need 10 milliamps, and then you select a resistor accordingly. Then you are getting maybe approximately 10 milliamps. If you are doing this one, maybe it is okay. But then if there is a fluctuation in the current, this current here can change it, or even voltage can slightly vary. Even with respect to temperature, this resistance can vary. Then what will happen is this laser diode will be damaged. So then you need a very good current source. Using a transistor, you can design a current source, but again, that is not as good as using a transistor and op-amp combination. So usually people design current source something like this. So what they do is you can use NPN or PNP. So this is using a PNP. So they have got an operation amplifier. So this is the operation amplifier. In the operation amplifier, output is connecting to us the base. So this is your base of the transistor. And then this is the emitter, this is the collector, because this is a PNP transistor. And then this is your laser diode. and then from the emitter you got a resistor R, and then that is going to the power supply because this is a PNP. Then from here you got a negative feedback, and then positive they have got 10 volt. So that is a reference voltage. So we call it as a reference voltage. And then this is a ground because this is for the power supply. So this one is again, we are connecting to the power supply. So these are the power supplies. And then this is an example of a design. Then how to design, I will show you in the next lecture. So you have seen something like this, and then this is a constant current source you can make using operation amplifier and transistor combination. Then if you see something like this, again this is a circuit. So we are studying this current source to understand more about operation amplifier circuits. So when you see this current source, somebody said I can find out the current, the required current. Say this laser diode requires maybe 100, say 200 milliamps. Can you design? So what you will be changing? Okay, so when you change the resistance, so what value you need? Definitely you are right. Thousand megohm. No, that means it's open.
I think you should change the
1000 ohms. Okay. So then if I were you, so this is 10 volt because you got negative feedback. What is the voltage here? Yeah, then you already got 10 volt. Then 12 volt minus 10 volt, so which is equal to 2 volt, and then divided by this R, which is equal to 200 milliamps. So your R equal to 2 volt divided by 200 milliamps. So then how much is it? 0.2. So which is equal to 10. So if you put 10 ohms here, then what is happening is you are getting a 200 milliamps current is coming here. Then 200 milliamps current is coming here. Then you might think some current will go to the input of the operation amplifier because that current is negligible. It's very, very small, like nanoamps. So that the remaining 200 milliamps will come as here, and then it will come as a collector. See, it's easy to analyze this circuit. Then, in order to explain properly, we will design one. So we can use maybe NPN. So we are going to make a current source. So this is positive, negative, and then we are going to use a NPN transistor, which is easy to explain. Then I am going to connect a laser diode here, and then I am going to connect a resistor here. Maybe I can connect here, and then maybe this is a power supply. From here I am going to connect to a V reference because this voltage should not be changing. Maybe that is equal to 10 volt. And then this is a power supply for the op amp, positive, and then this is maybe negative supply, and this is a positive supply. So this is also is a current source. Then how it is a current source? Why? Because if you set this 10 volt, then op amp will make sure that this is equal to 10 volt. And then how much current it will be flowing through? Our assumption is our collector current is approximately equal to emitter current because base current is in the microamps. Then 10 volt divided by R, that is a current through the ID. So ILD, the current through the laser diode, which is equal to ILD. So current through the laser diode is determined by this resistor value. See, and then this current will be constant. Yeah, that's the part I want to. You can connect a resistor here or not. This is just for understanding. Then now the question arises: how do you know this is definitely setting the current using R? There is a feedback. But then we got lots of circuits, like we got transistor, we got op amp, we got resistor, and then we made a current source. So how do you check if it is a current source? For the current source, the current should keep constant. How do you check it? Then due to some reason, could be due to power supply or due to temperature, due to some reason, this current, so this current you have set, maybe this R equal to 1 kilo ohm. So what is the current? 10 milliamps, because 1K, 10 volt divided by 1K. So then that is equal to 10 milliamps is the current flowing through the laser diode, that is a requirement. Due to some reason, I am going to exaggerate the value. Due to some reason, 10 milliamps suddenly became 15 milliamps. Then what will happen? Then when it is become 15 milliamps, the 15 milliamps will immediately flow through the laser diode and then it will come through and then drop here. Then what will become 10 volt will become how much? 15 volt immediately. When this one becomes 15 volt, but then this is only 10 volt, then what will happen? Op amp will reduce this current because the negative is more. When this base current is decreased, then what will happen is this collector current will decrease, and then in such a way that it is only 10 milliamps, so that this both voltages are same. You know what I meant? So if 10 milliamps reduced to maybe 5 milliamps, then what will happen is 5 milliamps will come here. Then now how much you got is only 5 volt. Then when it become 5 volt here, this is 10 volt. Then op amp has to adjust this equal to 5 volt. Sorry, this equal to 10 volt. Then how it will adjust is this is positive, this is negative, so it will increase the base current. So when it is increasing the base current, the collector current will increase in such a way that this voltage equal to this voltage. So that's the reason it is acting as a current source. So this is a very good circuit, so that you also get some idea about the current source, plus you also know how the op amp is kind of, the virtual short is functioning. That is the reason, if you know the concept of virtual short, maybe around 75% of the circuit, op amp circuit, you can understand using the idea of virtual short. So that's how it is operating. So this is just an example, so that you get a bit more understanding about the feedback system. So I have got some slide. So that's a feedback example which I discussed, and then when this is a 10 volt, this also is almost 10, and then you can set this resistance accordingly, which we already discussed. And then this one is with a different reference, so you can adjust the current either by this RE or by varying this V reference. But then here you need a requirement that this voltage should be a constant. So here the reference voltage, and this reference voltage either you can derive from a Zener diode, because Zener diode can give you a reference voltage, means that will not fluctuate that voltage. Or you can buy reference ICs. These days you can buy so many voltage reference ICs, because this voltage is fluctuating, means then the entire thing will fluctuate. So you have to make sure that this voltage is constant. Mostly people use a Zener diode. Means when you come to my drawing, here this voltage we are setting, because this voltage is a crucial one. So here maybe you can put a Zener diode, and then this is a maybe this is 10 volt, rated to 10 volt, and then from here you can connect a voltage source, so that this is 10 volt always. So then that, I think maybe this much understanding is sufficient for designing the circuit using op amps. Then there is one more concept, that is a differential amplifier and instrumentation amplifier, that we will study later, because you have to start filter designing from today onwards. You will be designing some filter in the lab. So as I said, we have opened a new lab on Thursdays from 5:15 to 8:15. So if you haven't allocated a lab, you will be able to enroll to that lab. So it might take some time to open it, like maybe 1 or 2 hours. So filters, another application of operation amplifier is filters. So why we have learned operation amplifiers? Because in order to design DSO, you need operation amplifier concept. Then in order to design filter, you need operation amplifiers, because filter is a part in your DSO design. Then filter, what do you mean by filter? Filter response. A filter is essentially a circuit which provides frequency selective or frequency varying gain or attenuation at its output. Means usually a filter means it is filtering some frequency competences depending upon the way we require. In the S domain, if you like maths, in the S domain, a filter has the basic form Ys, which is equal to GS or GS equal to Ys by Xs. You might have learned in the signal processing, where GS is a filter expression in S, which is equal to sigma plus j into omega. Omega is the frequency. So if you are interested in maths, but we will be looking at from the electronics point of view. And filter applications. So signal frequency selection. So filters, you can find band pass filters, band reject or notch, low pass, high pass. Then we use filters for noise mitigation. You can filter out the noise, phase locked loop, power supply, EMI filtering, RF tuning and oscillator tank circuits. You use a lot of filter concepts in the RF design. Then filters, when it comes to audio, you will see the application of filter. So this is, have you seen the three-way speaker pair? So you can see that you got three woofers here. So this is called three subwoofers. Then 1, 2, 3. Why they need 3? Because each frequency range, as I said, your audio range is 20 to 20 kilohertz. The audio amplifier design is always challenging. Now also you have to pay a good amount of money if you want to buy a very good audio amplifier. The challenge is still there are a couple of startups even in that range because of the challenge. The challenge is it is very difficult to amplify signals from 20 hertz to 20 kilohertz properly without noise. And again, even if you are successful, then when you connect to this woofer, what is happening is this woofer performance is again depending upon the frequency. Because if you connect, see, subwoofer 20 hertz to 80 hertz, means if you connect 2 to 20 kilohertz to this subwoofer, the performance will not be good because you are vibrating the frequency and then the vibrations are coming. So there is a dependency on the size of the woofer to the frequency. So then if you are using one woofer, that is not good. Then somebody found out, yeah, we can use 3 woofers of different sizes. Then how can you, then you might be having, how you can design the circuit. You may have the amplifier. From the amplifier, you got the entire audio signal from 20 hertz to 20 kilohertz. Then you can have 3 filters. And then one filter that is from up to here, 20 to 80 hertz, maybe this one, 80 hertz to 2 kilohertz, another one. And then 2 to 20 kilohertz, another one. So that then you connect to these 3. See, it's an application of filter. Then filter parameters. So when you design filter, people will ask you, what is the pass band ripple in your case? What is the stop band ripple? How much is the transition region width? Then pass and stop band edges. So people often say pass and stop band edges, but mostly people say transition region. And then selectivity factor or filter decay rate, phase response. So these are the important parameters you have to consider when you designing a filter. These are the primary characteristics by which we as designers judge the suitability of filter profiles. So based on these parameters. So when it comes to filters, there are 2 types of filters. One is a passive filters and another one is active filters. In the RF domain, mostly passive filters are used. Passive means you don't need any power, using passive components like resistance, capacitance or inductors. So passive filter, if you are interested in the transfer function of a filter, then this is the expression which we will not be using. We will be using simple equations because we are going to use active filters. Then passive filters, circuit using RC, RL or RLC circuit. So you can make a filter. For example, this is a low pass filter. Here you have used R and C. When you are using R and C, V out by V in, you can write out. You can write it. When you write V out by V in, which is equal to impedance across the capacitor, that is ZC divided by R1 plus ZC, because it is forming a voltage divider. which is equal to ZC, which is equal to 1 by S into C, S equal to j omega, divided by R plus 1 by S into C, which is equal to, because this impedance is frequency dependent, or 1 by 2 pi FC. But then we write as SC if it is a sinusoidal signal, which is equal to 1 by SCR plus 1, which we already studied in the ECD. So at least you have to remember up to here. So when you have a capacitor, you have to take into account the impedance of the capacitor, and then this impedance is frequency dependent. So because of that, you get a filter response by including inductors in the design. So this is made of resistor and capacitor. You can also include inductor in the design. Then filters with any desired flatness of passband combined with the sharpness of transition and steepness of fallout outside of the band means you can get a very good transition region, like sharp regions, if you are using inductor as well. If you are using, but then inductor, when you are using inductor, is a bulky component. So that's the reason most of the time people don't use inductors. Then resistor and capacitor also you can make passive filters. Then why do we need active filters? So we are interested in the active filter. So passive filters, we are using RC, RL or RLC. Maybe you are happy to buy inductor and use it. You got lots of space in the PCB. Then this is a passive filter. Then we can make active filters. Active filters means you are using operation amplifier for designing the filter. So this is a simple active filter. So in this active filter, what you did is you took the passive filter and then connected to the non-inverting terminal of this amplifier, and then from this itself, this is an active filter. People call it as an active filter. Definitely we can call it as an active filter, but not a very good design. This is an active filter. Then why we are doing this one means this, when you have voltage here, say you got 1 volt here, will you get 1 volt here? Because depending upon the frequency, if it is low frequency equal to 0, then you can get 1 volt, because then the capacitor, impedance equal to infinity, because this is kind of open. But when it is very high frequency, the capacitor will short it, because high frequency components will pass through the capacitor, because impedance equal to 1 by 2 pi FC. And then that is the reason when you are using an operation amplifier, you are compensating whatever losing here in the signal. So in that way, it is an active filter, because you are compensating the attenuation of this filter using an operation amplifier. But then this is not a very good design, because here we are not using op amp. Here op amp is not part of the filter. You know what I meant? You got the filter, passive filter, but then you are solving only one issue. But then we have different filter designs. Then before that, we will explain the difference between passive filters and active filters. For the DSO, please don't use the passive filter, because for DSO, we give you the option to design your filter. It could be different types of filter we will be discussing. You can design one filter design, you can pick it up. Somebody else may pick it up some other design, but then please don't use the passive filter. Passive filter is not not good. It will attenuate. So you have to design active filter. And then you can decide, we will be teaching you different types of active filters, then you may pick up one active filter. Then when you pick up one active filter, again it is your decision which order you should be using, 2nd order or 4th order or 6th order. You have to decide, you have to make a decision. Then we will teach you what do you mean by the order. Then firstly you should know, somebody will ask you, why are you not using passive filters? Why do we need active filter? Because when you are using active filter, you are using the power, then you are using more area. Then loading problem. The first problem with the passive filter is loading problem. As I said in when you are connecting this part to somewhere, maybe an operation amplifier or somewhere, what will happen is some signal you are losing here because of the loading. Impedance is not very high. It will attenuate. Actually, because of the drop across capacitor, you are attenuating the signal. Then if you want a very good design, you need inductors. In the lower frequency, 1 Hz to 1 megahertz, the inductor values become very large. When you calculate, if you are designing a filter of your frequency range, your interest range is 1 Hz to 1 megahertz, then the inductor value becomes very large, the inductor itself gets very bulky. So low frequency inductors are very bulky, making economical production difficult. Then it will become expensive. But then when you take active filters with operation amplifier, no loading because of high input resistance and low output resistance of op amp. Then op amp based design can provide gain and hence no signal attenuation. So even if you are attenuating something, you can compensate with the gain of the operation amplifier. You don't need any inductors. So this is the reason mostly people use active filters. Then passive filters. So passive filter means when you are using only one resistor, one capacitor, then that is called first order filter. And then if you want to, then if you are using a first order filter, your filtering may be not that good. Then you can use 2 stages if you want a very good filtering. So this is called a second order filter. So you are using 2 capacitors, so then it's called a second order. So when you are using first order filter, FC, cutoff frequency, equal to, already we studied 1 by 2 pi into RC, which is equal to 1 by 2 pi if your resistor equal to 4.7 kilo ohm and your capacitor equal to maybe 47 nanofarad, then your cutoff frequency equal to 720 hertz. So this is a low pass filter with cutoff frequency 720 hertz. Phase shift we already know, tan inverse 2 pi by RC, which we already studied. Then when you have 2 stages with the passive, then so this is the first order, so this is the second order. When you have 2 orders, which is equal to FC equal to 1 by 2 pi R1 C1 R2 C2 hertz. So you have to take into account, it is very difficult to match R1 equal to R2, difficult to match C1 equal to C2 exactly. And then that is a cutoff frequency. And then there is an attenuation. Your attenuation equal to 1 by root 2 the whole raised to n. Means if you got a second order passive low pass filter, means 2 stages, the gain at the corner frequency means at FC, then what gain you will get is, here you are getting you are connecting 1 volt. If you are connecting here 1 volt, you get only 0.5 volt here. So you can find out, so that is 1 by root 2 the whole raised to n, that is the passive low pass filter gain. Gain means actually you are attenuating, this much will be lost, because 1 by root 2, how much is 1 by root 2, which is equal to 0.7071. And then when you have 2 stages, 0.7071 into 0.701, which is equal to 0.5, means minus 6 dB. So what it said is, when you have 1 volt here, you will get only 0.7 volt here. So that is attenuation. You can find out. Then when how will you find out? Using this equation, 1 by root 2 the whole raised to n. Here n equal to 1, because this is first order, and then this is second order. So people sometimes use order as the pole, 1 pole. So this one got only 1 pole, POLE pole, because it's got only 1 capacitor. This is a second pole, it got 2 poles. So the or 2 order or 2 poles, people will be using 2 poles, that means 2 orders. And if you are using a third order filter, if you connect to 1 more stage, then your signal will be attenuated to 0.35. If you are connecting 1 volt here, after 3 stages you will get only 0.353 volt. So that is attenuation in the passive filter. Then idealized filter response. So when you are designing a low pass filter, people like this type of step functions. So this is the ideal response. Low pass filter, high pass filter, see the transition is kind of very sharp, step functions. Band pass, step function, notch, step function. But you don't get these type characteristics when you design a filter. But our aim is to get this one. So in order to get this one, you may need infinite order or infinite number of poles. Then you can get these type step function. So filter response, which I already said, this is maybe a good chart from the this I have taken because I like this chart. So when you have different frequency components, see high frequency and then you got low frequency, but the amplitude is same. So high frequency to low frequency. From low frequency this way high frequency. So if you got a low pass filter, what will happen is your low frequencies will be transmitted, high frequencies will be attenuated. And then if you got a high pass filter, it will only pass high frequency, so that this low pass frequencies will be attenuated. You will get a signal like this on the oscilloscope. If it is a band pass, it will only pass only in the middle some band. So that is the reason here it is attenuated, only this part will be transmitting and then it will not come here. If it is a band stop, then it is stopping some band so that it is taking off something from some region depending upon the design, and then you will be getting something like this. Then ideally you want a step response, but then when you design a low pass filter, mostly what will happen is you will end up having something like this. See, some fluctuations here, small fluctuation, then you get a transition region, not very sharp. Then here also sometimes you get some fluctuations. So but then some, depending upon the filter configuration, sometimes you don't find this one, but you will find this one maybe little bit some fluctuation. So this is called a pass band ripple, because in the pass band, because this is a pass band, then you are getting some ripple. So this ripple is important. Why? Because this ripple means your gain for this frequency is this much, for gain for this frequency is reducing, you know what I mean? So we don't want ripple here. It should be as minimum as possible. Then transition region, when you say cutoff, I want to cut off 1 kilohertz, then I don't want anything beyond 1 kilohertz going into the circuit. For that, this transition region should be as sharp as possible. But when you are designing, this transition region is not going to be sharp. It will be like with a big slope. So this region is called a transition band. So transition band, if you want to make very precise, sharp, you have to increase the order of the filter. Then stop band. So this is called a stop band. See, here all the frequencies, we are going to stop it from here. See, this frequency range. And then you don't want to gain in the stop band. So this should be flat. Because if you are getting some oscillation here, means the gain, you are getting some gain for the unwanted frequency. So that is called, this one is called stop band ripple. This is called pass band ripple. And then you don't want anything here, it should be flat. Here also it should be flat. And then this transition region should be as sharp as possible, not with a big flat. So when you plot gain versus frequency, we already studied body plots. A body plot, as in the previous graph, is an excellent way to immediately understand how the spectrum of your input signal will be affected by a filter. That generally they come as a pair with the gain. We are already familiar with these equations in the previous lectures I just showed you, and then the transfer function. Then body plots, maybe this is an example. So we will be, when you plot body plots, please make sure that you plot from using the logarithmic scale in the y-axis dB, and then this is the frequency, and then this is see, you can see 3 dB points. This is the 3 dB points. This is for a low pass filter, and then this is the pass band, means all the frequencies are passed through, and then this is the stop band. See, stop band, it is ending here. See, this much frequency is still going into your circuit, and then because you got this big slope. If you can design one with from here it is coming straight down to here, that is the ideal filter. You won't be able to design it. So you always will have some kind of slope because of the region, the stop band, some frequency components, this much is going into your circuit. And then we also plot phase. What is the phase of the signal? Because filter, you have to find out the phase. See, when your frequency is increasing, ideally the phase also should be constant. But then what happens is when your frequency increases, then the phase of the frequency components, you know what I mean? So this one means your gain, this is equal to your filter here. This filter doesn't have any gain. It's a unity gain filter. You may have got an amplifier, then you want to take out the high frequency components. Then you are having zero gain filter. You got a gain 0 dB, that is equal to 1. Unity gain filter. Then when you look at here, gain equal to 1 for 0 hertz, gain equal to 1 for 10 hertz, gain equal to maybe again 1 for 100 hertz, and then maybe this is equal to 1k, that is your cutoff. Up to 1k, your gain equal to constant. After that, 1k is our interest. We don't want anything beyond 1k, but then because of this slope, still 1k, maybe up to maybe 2k signal will pass through because of this region. And then we also see the frequency components. In the frequency components, as I said, when you take Fourier transform of your signal, there are so many frequency components. And then for all the frequency components, the phase should be same. But then what will happen is when the signal is passing through the filter, you will be seeing some phase shift. Means for when the frequency increases, your phase maybe shift is minus 45 degrees for high frequency components. You know what I mean? So different frequency components has got different phase shift, which is not good. We have to be careful. And see, when it comes here, it is around minus 90 degrees. But the phase shift is 180 means you have to worry. You know what I meant? What will happen when the phase shift is 180? There. So if you got a negative feedback, the negative feedback will become positive feedback if you got a phase shift of 180 degree. So we will study that later. So when you, that is the reason when you design a filter, we will be plotting gain versus frequency and then prove that it is a low pass filter with the cutoff. Then we will also plot the phase with respect to the frequency, because we want to see the phase of the signal is inverting or not. See, up to here, this is the cutoff frequency, then it is around 45 degrees. Then that is okay, acceptable limit. 45 is okay. Then you also will see analog filter and digital filter. But then we will be studying analog because we are using analog filter in the DSO design. Filter implementation can be done in either the analog or digital domain. Analog, fast, you can make it very fast. Often the more economical choice at high RF frequencies, especially at RF frequencies, nobody will use digital filter, but analog can be simpler to design and implement. Filter design in the analog domain is not very difficult. Digital, matched channel performance is very robust, but then the problem is the limited frequency response. In the analog you can have very high frequency, fast, but then this got some limitation with the digital components. Component tolerance no longer an issue. When you have analog design, so then which one you will be choosing? If the component tolerance is an issue, maybe you should go, because that is your first priority. You don't care about the bandwidth, you don't care about speed, but the component tolerance is an issue, you should go for the digital. If speed is an issue, you should go for the analog. If price is the factor, you should go for analog. But then digital filters are more complicated to design and implement, but analog ones are very easy. With faster, cheaper and more sophisticated DSP electronics, digital filtering is gaining dominance in highly integrated audio, video and RF applications. Having said that, these days you can find faster and cheaper and more sophisticated DSP electronics so that you can design digital filter. But for DSO you don't need digital filter, we will be designing analog low pass filter. Filter implementations. Filters can be implemented in a number of ways, each of which have their own unique advantages and limitations. So passive, active, because active means requires power sources. So digital, if you are in the digital FIR, finite impulse response, infinite impulse response, switched capacitor bank, where you don't have to study. Analog, which we already studied, passive and active. Number of poles or number of orders. So this is an important graph. The polynomial order or the number of poles determines the roll-off rate of the filter. See, roll-off rate, this is the roll-off rate. One pole, because this is the ideal filter response. If you say that you are designing a low pass filter with a cutoff 1 kilohertz, for example, so this is a 1 kilohertz. See, from here straight down, so that nothing beyond the 1 kilohertz will go. As I said, if you want to make this one, you need infinite number of poles or infinite number of orders. So when you are designing one, then if you are designing a one pole, and then if you are plotting in the body plots logarithmic scale, one pole, first order, filter has a roll of minus 20 dB per decade. So means this roll off is minus 20 dB per decade. So 1 kilohertz. But then still it will be going not only 1 kilohertz, 2 kilohertz, but attenuated, 3 kilohertz, attenuated, 4 kilohertz, attenuated into your circuit. But then you can increase it to 2 poles or 2 orders. Then you will have roll of minus 40 dB per decade. See, it is bit more sharp. If you go for a third order or 3 poles, then it got minus 60 dB per decade. See, and then if you go for a 4th order or 5th order, it will be much more sharper. But then if you want a vertical line, you need infinite number. So there is no point in having a very high number. So, but then when you design your DSO, as I said, you have the choice whether you want first order. You can't design it because you are using active filter. Active filter, the beginning is second order. I will come to that point. Then for DSO, it's up to you whether you want 2-pole, 3-pole. 2-pole, you are getting something like this, minus 40 dB per decade, minus 60 dB per decade if you are using 3-pole. So you have to keep in mind the space, because the board size is fixed. You can't have more size. Then also the number of components may be okay, because you can get more components, but the space is an issue, because when you design a second order filter, you need one op amp. If you are designing a third order is not a good idea, because using another op amp you can get fourth order. The first order filter you can design using a symbol R and C, resistor and capacitor. So for the DSO you may have options 2-pole or 4-pole, but then you have to keep in mind the space of the DSO board. So you have to make a decision, plus what extra thing you are going to design. Maybe you got some space, then maybe you can design a fourth order filter and then you are using some space, or you want to leave that space for your innovation. You know what I meant? So you have to make a decision. Having said that, many students in the last year used 2 poles. Only some used higher poles. So second order might be enough for you, but it's again up to you. So number of poles. So how will you design a second order filter? So second order filter means, as I said, RC component, and then so then here you got to see 1 pole minus 20 dB per decade, 2 poles minus 40 dB per decade, 3 poles minus 60 dB per decade. So then we are going to design this one, minus 20, minus 40, minus 60. So minus 20 is a 1 pole. You need only 1 pole. So then you use a simple RC filter and then use an op amp for amplifying. So that is called, this is how many orders? This is called only 1 order, because here RC, because you are going to use RC filter. Here this is just an example of filters. This is an RC filter. You are using only 1 operation amplifier, but when you are using 1 operation amplifier, we can design second order filters that we will study. So this is just an example. When you are having an RC filter, you are connecting like this. So here you got a resistor, here you got a capacitor, then you are using this operation amplifier only for amplification, means that to compensate the attenuation. Then this is a first order filter, and then this is minus 20 dB per decade. Then you can design a second order, then you are using 2 stages. Then 3, when you are using 3 operation amplifier like this with RC, then you are getting minus 60 dB per decade. So that's how the pole, here you got 3 poles, 2 poles, 1 pole. But then these designs are not at all good. Why? Because here you are using your operation amplifier only for compensating the attenuation. So that is the reason you are getting only 1 order from out of this. But if you can cleverly design, or if you follow the standard designs using 1 operation amplifier, you can get 2 orders, not 1 order. That we will study such filters. Then cascading and order. So filter may be cascaded to increase the overall S domain polynomial number, like the number of orders or poles, and shape the filter frequency response. You can make it very sharp. So when you are doing, usually this is how people are ordering. First order, A equal to 1. Second order, something like this. When you have third order, then people have confusion which one to connect first. Mostly they will connect a first order first and then second order. Then fourth order, two poles. Then when you have fifth order, they will be connecting a first order filter here, second order filter here, second order filter here. So this way is much better in terms of getting sharper transition region. Sixth order, there is no confusion. So fifth and third, you have to be careful. If you are making a third order filter, you have to connect first to the first order filter. That may be a symbol R and C. Then you have got an op amp based second order filter. Then filter, we already discussed, this is from the art of the electronics. This is a low pass filter. See, the frequency is coming up to this point and then this is decreasing. And then simple example is using a resistor and a capacitor. It will give you a low pass filter. With op amp, you can design something like this. Then it is an low pass filter. So I'll come to this design. Then high pass filter, it will be transmitting only high frequencies and then attenuating low frequencies. And then you can design using a simple capacitor and resistor. then again you can use either op-amp combination. Then what you have got is a general type of filter. See, something like generalistic filter. Then you can have something like this. You can combine both, and then you can get it's kind of a general type of filter. You can see from here it is coming, then it is attenuating, then it is keeping constant. If you have some different application, again you can use it. So while coming back to this circuit, it's very simple to analyze the filter circuits. When we come to this circuit, how can you say that this is a low pass filter? So you can immediately find out whether it is a low pass or high pass. So we will go to the first passive filter. So when you have a resistor, when you have a capacitor, so this is a circuit, this is a V in, this is a V out. Then so this capacitor, see, impedance of the capacitor equal to 1 by 2 pi Fc. So this is R. So then I am going to plot it. So this is a dB gain, V out by V in versus frequency. So V out by V in dB. Then I can easily find out. So F equal to 0. Then what will happen is your impedance equal to infinity. So Xc tends to infinity. So this is open. You know what I mean? So that whatever the voltage V in, you get V out here. So that is the reason you are getting something like this. Then when F equal to infinity, what will happen? Your Xc tends to 0. Because impedance 1 by 2 pi Fc, when F equal to infinity, your impedance tends to 0. Means this is shorting. Then all the signal will be shorted to ground, so that at high frequencies the gain will be small. In between you will be getting something like this. See, it's a low pass filter. Same with when you take high pass, you will be connecting capacitor here and then resistor here. Same principle. When you have F equal to 0, what will happen? Your impedance equal to infinity, so that it will not pass anything. So the low frequency components will not pass through, because your capacitor is kind of open circuit. And then when the frequency is very high, infinity, what will happen? Impedance equal to 0 means it will be a short, and then it will be going, and it is dissipated across the resistance. So that is the reason you are getting something like this for the high frequency. Now when it comes to op-amp based design, again you can apply the same principle to find out which type of filter. For example, you got something like this. So that design is negative, and then you connected positive here from the art of the electronics. So that's a different ways you can design filter. Then you got a capacitor here, then you got a resistor here. So then this filter, and this is a low pass filter. How can you say this is a low pass filter? So this looks like an amplifier. It's an inverting amplifier plus a capacitor C. They connected in parallel. So this is actually is a low pass filter. So it will give a, if you characterize, you will get something like this. This frequency, this is the gain. How can you explain? Again you can put F equal to 0. Then what is the impedance of the capacitor? So Xc equal to how much? 1 by 2 pi Fc, which is equal to infinity. Then when the frequency equal to 0 means low frequency components including DC, this capacitor is open. You know what I meant? Because Xc equal to infinity means this capacitor is open. So then it is acting as an inverting amplifier with the gain provided. So this is R2, this is R1. So your gain equal to minus R2 by R1. So that's the reason you are getting a gain. But then when F equal to infinity, when you have very high frequencies, then Xc, what is equal to Xc? Then what will happen? This is shorting, so it is acting as a buffer. So then your gain will be reducing to 0 dB like here. In between you are getting something like this, the transition region. You know what I meant? So by putting two conditions, F equal to 0 and F equal to infinity, you can get an idea of what type of filter it is. This is an example. And then we will go to the other op-amp. So this is a low pass filter. And then so when we go to the other design, there is another design. Again what that does is same configuration, and then here negative feedback, then you can have a capacitor, then you can have a resistor here. So this is a high pass filter. So high pass filter means this is a gain, this is a dB, and then this is a frequency. So it will be something like this. It will attenuate low frequency. Again because of this capacitor, see this is a simple design. It's a high pass filter. means again f equal to 0. When you put f equal to 0, your impedance equal to infinity, means this circuit is open, so that you don't get anything here. When it is high frequency, this will be kind of a short, then it's acting as an amplifier, so that's the reason. So we can analyze. So this also can help you to design some filter of your own from the op amp using this condition. Maybe you can think of designing a band pass using the op amp, and so that's how we will be analyzing the filter, and then we will be studying some filter configurations or topologies like Butterworth filter, Chebyshev filter. Then when it comes to filters, the filters low pass filter, high pass filter, band pass filter, and band reject filter. So these are the basic, big top level classification based on the functionality. So based on the functionality, so this name is very important because there are other classifications. Based on the functionality, you will see low pass, high pass, band reject. So, but then under this low pass filter, there are so many different types of designs. Like Butterworth filter, that's a low pass. Chebyshev filter, and then again in the high pass you will see different names. But those are depending upon the type. So these are based on the functionality. This is a top level classification. And then under the active filters, then you can have active filters. If you take a low pass filter alone, under low pass filters you can have Butterworth filter, Chebyshev filter, inverse Chebyshev, Bessel filter. See, different types of filters. Again for your DSO, you have to choose which one you want. For DSO you need a low pass filter. You can have a Butterworth filter, you can have a Chebyshev, or you can have inverse Chebyshev, you can have Bessel filter. And then when you choose the filter, you have to be careful. Then for the Butterworth filter, you can see Butterworth filter, the frequency response, the best amplitude flat response in pass band. So if you are looking for a flat response in the flat band, see, pass band you got a flat response. Then this is a very good filter. Chebyshev, built for equal amplitude ripples in pass band. See, it will get some ripples here, so it's not good. Inverse Chebyshev, built for equal amplitude ripples in stop band. See, here you get some inverse Chebyshev, means you are getting ripple here. But then here, transition slope attenuation is steeper than the Butterworth. So here you don't have the ripple, but then this transition is not that great. But Chebyshev, you got a little bit ripple here, but then the transition is much better than the Butterworth. You know what I meant? So each one got its own strength and disadvantages. Bessel, almost linear in pass band, but very poor transient slope. See, Bessel filter means Butterworth is something like this. Bessel means, see, it is coming like this. But excellent for pulse generator circuits since they minimize the ringing and overshooting. So Bessel also got some application. But then from here, now you know that maybe the best one might be, one of the choices might be Butterworth for the DSO application than Chebyshev because of the ripple. But then I wouldn't say that you should design a Butterworth, but then because we have got other designs as well, simple designs, so you can adopt that design as well later. Then when it comes to filter, we study a factor called quality factor. Maybe I'll stop here and continue in the next lecture.
I got one question about this. So in this lecture, you said peak has to be linear.
No. Actually, if you take A1 equal to infinity, you will get the requirement. But sometimes what will happen is this K equal to R2 by R1 plus R2, and then K in the A1. So, but then when you have A, but then the A is not very high, then you can compensate that with K. You know what I mean?
In this case, we normally got large A.
Yeah, in this case, it's not applicable. K, you can neglect that.
Yeah, but why is this one necessary?
No, it's not necessary. The K equals to infinity. Why? Mainly because A equal to infinity.
Yeah.
But then I mentioned this K because we studied the loop gain.
Okay.
Yeah, loop gain also is infinity.